Because in essence, all I'm doing is I'm going to go over all the different rules we talked about, and then we're going to do some problems, and we're going to figure out which one we should use. Because that's the only thing that we haven't actually done so far. I've shown you all the rules, we've used all the rules, but we're kind of using them in like that section. So it was like you knew on class on Tuesday that we were going to use the ratio and the root test. So it's like you weren't thinking about, oh, I have to do the integral test. So you knew we had to do that. So we're going to look at some problems that make you actually think about what we're actually going to be doing with them. So, all right. So there are 8 stages or rules and stuff that we've talked about. The first rule that you should always look at is the test for divergence. So basically your test for divergence, you're looking at the sequence. So if the sequence does not go to 0, it diverges. You're done. All right. So when you're looking at them, these are the types of problems where you have, like, say, just for example, it's 1 over n. You know that one's going to convert. That one's going to go to 0 because the bottom's bigger than the top. If you had a over n, so that's converge. If you had a over n squared over 5, you know that one diverges because the top's bigger than the bottom. All right, so those types of things. So it's like that's when you're looking at the test for divergence. If you can quickly look at this sequence and go, there's no way that's going to 0, you're done. You don't even need to go any further in the problem. If it does go to 0, so actually that one technically doesn't converge. I shouldn't say that. Not divergent, which is different than converges. If it goes to 0, then we have to look at some other things. So that's one of those ones that it's really quick and easy for you to look at first and then move on. Okay. And a lot of your simple polynomial types problems, it's not. No, based on this test, we can't tell that it's not divergent because it goes to 0. This one goes to 0. So this test doesn't work. It is convergent. It is divergent, but it's not because of this test. So, but it's also not convergent. So I can actually, you know what? I'll just solve this problem.
Example of one that
I will just solve this problem.
test for divergence shows that it's not divergent, but it's not convergent.
Yeah, the harmonic series. The harmonic series goes to 0, but is divergent. So, and there, that just solves that. Makes I'll just do n squared. Yeah, but remember, the test for divergence doesn't tell you that. So the test for divergence tells you nothing about if it converges. It just tells you if it diverges. Okay. So just because it goes to 0, and actually I'll put can't use this test because it goes to 0. Okay, you have to try something else to be able to prove that it's convergent. Yeah, the harmonic series is a great example of one that does go to 0 and then isn't convergent. There's a bunch of other examples that I just can't come. That's the easiest one to come up with. That's the one they typically use as the example.
So it's not divergent. It's just you can't confirm that it's divergent using that test.
Correct.
Okay.
Yes. It's just you can't use this test to show it. Like this one, right? The one I've changed it to the P series. It is convergent. I just can't use this test to show that because this test doesn't show convergence at all. The next two to use that actually do show if it's convergent or divergent. It's the P series and the geometric series. So P series is the 1 over n to the P, or n to any power. So it's the exponent is the power, and the base is the variable. So n to the 3rd power, n to the 4th power, n to the negative 2nd power, things like that. You want it in the form of 1 over n to the np. So if I have 1 over n squared, that's convergent because 2 is greater than 1. If I had 1 over n to the negative 3rd, or actually, let me actually change this one. I'm just going to do n to the third power. That one, right as it is, I wouldn't even have to do the p-series because the test for divergence tells me it diverges. But if we want to look at this in terms of a p-series, that's n to the negative third power, and negative 3 is less than or equal to 1, so it's divergent. The geometric series has to be in the format of a times the ratio and then n to minus 1 or the n power. Both of them will end up working. It just depends on where you're starting. And then in that one, it's the ratio you're looking at. It's the R value. If the absolute value of R is less than 1, it converges. And if the absolute value of R is greater than or equal to 1, it diverges. So those two tests, you'll actually know if it's convergent or divergent. All right. Your comparison tests. Don't have to write down this whole big block of text. I have the comparison tests broken down in the next 2 slides. This is where we're looking at comparing it to another series that I already know. You have to choose something that you know. So in this case, the vast majority of the time that you're doing it, you're comparing it to either a p-series or a geometric series, because those are two that you can quickly look at and tell me if they're going to be convergent or divergent. There's 2 comparison tests we looked at. The first one was the direct comparison test. This is the ones where we looked at it's convergent if the original series is always less than the new series I'm comparing it to. And it's divergent if it's the series is always greater than the new series I'm looking at. So if you think about it like that squeeze theorem where you're squeezing it to the 0, if you know your series is above and my series is here, at some point it's got to squeeze down to 0, so it's got to converge. If it's always going to be bigger than it, then and this one diverges, the other one has to diverge. This test works really well if they go the same direction. If you can quickly and easily tell me that one is less than the other or one is greater than the other. If you cannot, that's where the limit comparison test comes into play. The limit comparison test doesn't need to know which direction it goes. Okay, so it doesn't need to make sure that one is always less than the other one. So if you can't look at it and go, yes, this is always going to be less than it or always greater than it, use the limit comparison test. As long as it comes out to be a finite number, greater than 0, then they both do the same thing. And remember, the series that you're picking, you have to know what it does. It either has to converge or diverge. That's why we go back to that p-series, p-series and geometric series. Limits 4. The comparison tests are all 4. Comparison tests, there's 2 different types of comparison tests, but they're all 4. 5's next. All right. Five is the alternating series test. This one works when it's alternating. So the first thing you have to be able to show when you're looking at the alternating series test is that it actually alternates. So we've looked at some examples in last class where they were kind of alternating, but they really weren't with like the trig functions. even if you have the -1 in front, you still have to look and make sure that the function actually does alternate. So as long as that's the only negative sign in the problem, it's going to alternate if it's the -1 in front. But if there's something else inside of it that doesn't force it to alternate, then we have to do a different thing. As long as it alternates, you can look for two things. The first thing is that the terms have to decrease. Okay. If you can't just tell by looking at it that it's decreasing, you're going to have to use the derivative rule. Take the derivative of it and find out where the derivative is negative. And the second thing is that the limit of the sequence goes to 0. I always like doing that one first because that's the test for divergence. If the limit of that doesn't go to 0, then I know it diverges. So I will typically always do that one first. So the first part is that it has to alternate. If it's not alternating, I can't even do the other two conditions. So that's why I always check that first. As long as it's alternating, then we can do the two conditions. And I always, the way they've got it listed here, I always like doing condition 2 first, because that's the test for divergence. So if it diverges, then there's no point in me figuring out the other part of it. If it goes to 0, then I got to figure out the second part. It does save you sometimes. All right. These are all in section 11.7, by the way. The only, like the top blocks are all exactly in section 11.7. I just copied the other parts into it. So I'll post this up on my site either tonight or tomorrow morning. Depends on what happens when I get home. Sixth one is the ratio test. So the ratio test is where I take and I'm dividing basically the second term, or n plus 1 over n, basically. And we're looking for the limit as long as that limit goes to something less than 1, it is absolutely convergent. And if it's absolutely convergent, then it is any series under that is convergent. These, you have to take the absolute value of the thing. You're looking at you're not looking at it if any signs in front of it. You're only looking at the absolute value of it. If the limit that you take when you do that is greater than 1, then it is divergent.
Is it also absolute divergence?
There's no such thing, actually. So if you're looking at that one, it's actually just the series of 8, that one you're testing. That's divergent.
So the ratio test and the root test are the two that can determine whether it's convergent and divergent.
The P series and geometric series can too, but yes.
Okay. Oh, right.
And the limit series can, depending on what you're testing it with. So yeah, basically the only thing that can't is the test for the divergence. The rest of them, as long as you meet the conditions, can tell you the two things. The problem is we need all these different things because not all of them meet the conditions. So they're all very picky on how things work. And if it equals 1, we don't know. We have to try something else. And on Tuesday, I showed you like the harmonic series and the P series. They both equaled 1 when we tested it. I know that the harmonic series diverges and the 1 over n squared converges. So they both went to 1. So that's why that doesn't give me any information. The root test is, one more thing. Let me go back to the ratio test real quick. The ratio test you want to use anytime there's any factorials in it or products that are raised to an nth power, so like an exponential function. those things. You typically want to use the ratio test for it. Ratio test works really well for those product type problems. The root test, this is where you're getting rid of something raised to the nth power. And the rules actually for the root test is exactly the same as the ratio test. If the limit is less than 1, it's convergent, greater than 1, it's divergent, and if it equals 1, it is inconclusive. Hello. All right. And the last one, the integral test. So as long as the function that you're looking at, or the series or sequence that you're looking at, can easily be made into an integral, or can be easily integrated, the integral test will work. As long as it's continuous, positive, and decreasing. Okay, so again, it's basically as long as they function, most functions are continuous, as long as it's continuous from 1 to infinity. So like, for example, 1 over x is not continuous. However, if we're looking at it in terms of this integral, it would be continuous because the discontinuity is at 0. So in this situation, that would be continuous. It's got to be positive, and it's got to be decreasing. And again, if it doesn't go to 0, therefore the test for divergence will take care of that problem. If the integral is convergent, then the sequence or the series is convergent. If the integral is divergent, then the series is divergent. So basically, if the integral goes to a number, that means it's converging on that number. Therefore, it's convergent. If the integral goes to infinity, then it is divergent. Let's do. All right, let's look at the problems I pulled out. All right, let's look at this one first. So take a couple minutes, look at it, figure out which test you would like to use for this one. Okay, what am I using the P? How am I using the P series for this one? All right, so we're thinking P series for this one. So P series is 1 over n to the P power, right? Okay, so in this case, that's 1 over n to the negative second power, correct? But what about that? And it's not geometric because geometric has the number in the base, and then the exponent is the variable. So that would be like 2 to the n power, 3 to the n power. Those would be the geometric series ones. And if I can't and we can't use any of the limit comparison tests unless I can somehow make this a p series or a geometric series, because those are the only ones that I know go to a specific thing. If you look at this one, honestly, like even doing like the root test or the ratio test, there's nothing, it's going to be very complicated to be able to break down. This one actually is the integral test. And you can look at it because of that. If I do U substitution on that, it gives me that. So if I take my f of x, I have x squared e to the negative x to the third. So I'm going to make u negative x to the third. So du is negative 3x squared. So I can pull over the negative 1/3 to the du side. So then I'm doing the integral of negative 1/3 e to the u du, which is negative 1/3 e to the u. And we're doing this from 1 to infinity. Oh, I got to change it first. I change it back to the negative x to the third. So if I plug in infinity into this, as that's a negative exponent, so that right there is basically 1 over. So it's 1 over e to the x to the third. So if I plug in infinity to that, that's going to 0. So my infinity part goes to 0, and if I plug in 1 to this, I get negative 1/3 e. So the integral test, as long as it's going to a number, it is, oh, sorry, it's not negative, it's positive because it's minus that. As long as it's going to a number, it's convergent. This is going over to 1 over 3e, which is a specific value. So this series converges. And we use the integral test. So on your test, if this was one of the questions, that's how I'd want to see the work done for it. That's what I'd expect to see. I expect to see that it's convergent or divergent, which test you used, and then the work for that test. All right. Any questions with that one?
So it's just that at the final end.
Yeah, so basically, so the integral test, if we go back and look at the integral test one we just looked at, so it's continuous, positive, and decreasing. If we look at this one, I know it's positive, I know it's continuous, and because that's down the bottom, it's decreasing. Like, I'm going to be pretty lenient on the decreasing part in terms of this because, like, You could sit there and go through and do the all derivative on it. But for the most part, they're going to be decreasing. Because if they're increasing, then it fails the test for divergence and we're done. So in this case, it's decreasing. So we do the interval. So we're looking just at the interval of it. The integral rule says if the interval goes to a number, so if it's convergent, which means it goes to something, therefore the series is convergent. So we use this rule right here. So it's the integral is convergent, therefore the series is convergent. Okay. All right. Try this one. All right. So what do we want to try? Test for divergence? Okay, so we're looking at the limit of this as it goes to infinity. So all right, let's say use K. So how am I doing? Huh? I, you can't divide. Okay. What do you mean? Okay. All right. So we're gonna scrap the test for divergence for a minute. We're gonna play around with this and clean it up a little bit first. Okay. Let's try that. All right. So I'm not gonna rewrite the summation symbols. So I have 2K times 2 to the negative 1 times 3K times 3 over K to the K. Okay. So that gives me 3 over 2. And then everything else is to the K power, right? So 2 times 3 is 6 over K to the K power, right? Because in essence, I'm taking that, and that, and making that. Okay. All right. So, and this one, if I was to do the limit on that one too, like the test for divergence, I would end up getting, remember the whole thing where if you're raising ever infinitely get smaller number to infinity, like as numbers getting bigger, it doesn't really tell me much.
Yeah.
I don't know if it goes to 0. So I really can't do the test for divergence on this one. But we have another thing that we can do to get rid of some stuff that might help us. If I ignored the first part, because remember one of the rules that we did at the very beginning was said that I can do this. I can pull out the 3/2. So I can just ignore that for right now. So what am I going to do with that 6/k to the kth power? Yeah, the root test gets rid of that k, right? So let's do the root test of this one. So if I do the root k to this, I'm looking at the limit as k goes to infinity of 6/k. And that goes to what? That goes to 0. With the root test, what does that tell us?
Less than 1. So
All right, so is 0 less than 1? Yes. So this is convergent. I'm not worried about you putting absolutely on there. It's fine. Convergence, fine. So you start to see that the hardest part of this test is not going to be doing the tests. It's going to be figuring out which test you need to use. One more at this one more in the final. All right, next one. So what do we want to try for this one? Yeah, so the first thing, whenever you see this, the first thing you should think of is the alternating series test. The only thing you got to be wary of is if there's anything negative after it. So like ln of n and square root of n, that can never be negative, right? Okay, so I know this is alternating. So let's try the alternating series test. Okay, so alternating series test we're going to use. Okay, so remember I always say test the limit part first. So let's do the limit part first. So the limit as n goes to infinity of the ln of n over the square root of n. If I go to infinity, both those go to infinity, right? ln of infinity is infinity, square root of infinity is infinity. So I have infinity over infinity. So what can I do? It is an indeterminate form. Yep. We're going to use L'Hopital's rule. So that means I take the derivative of the top and the bottom. What's the derivative of ln of n? Yeah, n. 1 over n. And then the derivative of square root of n is 1 over 2 square root of n. Because you have n to the 1/2, which is 1/2 n to the negative 1/2. So you get the 1 over square root. So if I clean this up a little bit, I end up getting 2 over the square root of n. Okay, I will actually write this out because so I have 2 square root of n over n, which goes to that. Remember, you keep, change, flip. It was. That's where I flipped it over. So this fraction there flips. All right, so now what's that limit go to? That goes to 0. All right, so we have, unlike most situations, we've determined that one was a little more harder than most of the limits that you're going to have to do, but it goes to 0. So that's one of the 2 cases that I have to test. The other case I have to test is that this is always decreasing, or at least decreasing as I get quite large. So to test that it's decreasing, because the numerator and denominator both change in this one you're kind of going to have to do the derivative rule for it. So let's take the derivative of it. So I'm going to make f of x ln of x over the square root of x. So we've got so you can do this as a product rule, as a quotient rule. It's really up to you how you want to do it. It doesn't make much difference. I'm going to do the quotient rule. It's actually a little simpler in this situation. So the top ln of x goes to 1 over x. Square root of x, which we just did, goes to 1 over 2 square root of x. I just leave it as x to the 1/2. So I have the derivative of the first is 1 over x times x to the 1/2 minus 1 over x to the 1/2, or 2 over x to the 1/2 times ln of x all over x. So this simplifies down, and there's a bunch of little steps in between that you actually have to go down and simplify this down to. But this simplifies down to 2 minus ln of x over 2 x to the 3 halves power. So we're looking at where this is decreasing. So we want to know when this is less than 0. Can my denominator ever be negative? Can the denominator ever be negative in this case? Okay, there is a reason I asked that question. Most of the problems that we've done, it hasn't come up into play. If it does, you actually would have to find the bottom when the bottom is negative, positive, and then look at the overlaps of them. I don't believe I put any of those on the test, so you don't have to necessarily worry about that. But there is situations where that does come up. That's why I always ask that question. Normally, it's the numerator because when you're doing the derivative of a quotient, your bottom is squared, which typically will get rid of any exponents you're going to have anyway. So in this case, it would have ended up being the third if it wasn't the root there too, and the root kind of takes care of any of your negative values.
So can we just do it with any equation? If it's one, it can't be negative.
What do you mean?
In the question, it says the summation like any equation, it starts from one. With a negative.
Right, you're not going to plug in negative numbers, correct? But sometimes there's a way, like say that 2 minus ln of x was in the bottom. That could be negative because ln of x can get bigger than 2. So in those situations, we'd have to look necessarily at the top and the bottom. In this situation, because of the way this it's set up there, you're right. I'm never going to have any negative numbers in the bottom, so I don't have to worry about the bottom. So I just have to worry about the top. So I have, in this case, 2 minus ln of x has to be less than 0. So I have ln of x is greater than 2. So we have e. So x has to be greater than e to the second power. Once it's greater than e to the second power, it's decreasing. Now, remember the thing I said, as long as it's going to initially or eventually decrease and never start increasing again, we're fine to use the test. So even though that's not at 1 or even at e, this is a little higher than e, it's closing in on 9. So even though it's that high, you're still fine. So since that's going, it is decreasing now we've shown, and the limit of it goes to 0 based on the ACT or AST, it is convergent. Now, the alternating series test does not explicitly state that you can find if a series is divergent. Okay? However, this right there is your test for divergence. It will, if it's going to fail a test, it's going to fail that one. Because if that's not going to 0, then the chances that it's decreasing, or if it's going to 0, the chances that it's actually going to be increasing as you get bigger is next to none because it's getting bigger. It can't go to 0 as the limit. So there is situations where that it does go to 0 and it's not decreasing. That can't happen. But it's never going to be fail the test for divergence and then pass it. Like it will never end up working that way. That's why I always do the second one first, because that's the one that's most likely to fail. All right, let's try this one.
Did you do a comparison test?
Comparing it to what?
Um, overdrive.
Okay. So my AN is tangent of 1 over n. And my BN that I'm comparing it to is what?
The 1 over n.
Okay. So do I know the order of these? So the question, so when we're comparing them, so this right here, I know diverges, right? Okay, so that gives me that information. So that means for me just to use the direct comparison test, I have to know that that is bigger than that. Is that true? Okay, so we can't use a direct comparison. So that means we have to do a limit comparison. Before I do the limit comparison, is there anybody else that had another idea? Guys don't listen to me very well, do you? Actually, it's a good thing in this situation because I was actually, so we did a problem on, I don't know if it was Tuesday or last Thursday, where I had sine of 1 over n. And we said you could just do the limit as n goes to infinity, and we can put the sign out and just do that as 1 over n. Remember that? Okay. It works in this one. It doesn't work in this one. Anybody want to take a guess why? Yes. Yes. Sine is continuous. Tangent is not. So I can't tell over this range, over that, if tangent is continuous. So therefore, I can't do this. This works if it's continuous. So that's why that doesn't work. So this one you actually do have to do a limit comparison test, and you're going to do the limit comparison test. We're going to take the division of it. So we have the limit as n goes to infinity of tangent of 1 over n over 1 over n. All right. If I put infinity into either of those, what am I getting? I'm going to get 0 on the bottom. And what am I going to get on top? 0. So I have 0 over 0, which is an indeterminate form. So since it's an indeterminate form, therefore I have to do the L'Hopital's rule. So take the derivative of the top and the derivative of the bottom. So the derivative of the top is secant squared 1 over n times, what is it, 1 over n squared, I think it was. Yeah. Negative 1 over n squared. Over negative 1 over n squared. So this ends up going down to secant squared of 1 over n. So the limit of secant squared of 1 over n So what's basically what happens as it goes to 0 for secant? Secant is the reciprocal of cosine. So it's 1 over cosine of 0, which is what is cosine of 0? 1. So this goes to 1. So that goes to 1. The limit comparison test says what? That's the root. Root and ratio test are 1. Yeah, it's the 0. So limit comparison test, as long as the number is greater than 0. So as long as it's greater than 0, it does the same thing. Okay, so it doesn't tell me if it diverges or converges. It tells me it does the same thing as what I'm testing. Since I'm testing, the one I'm testing it diverges, this one also diverges because 1 is greater than 0 based on the limit compare test. Okay, so the limit comparison tells you does the same thing. So since the one I tested it to diverges, that means the other one diverges. If for some reason you chose the wrong thing for b to the n here, the reason that 1 over n works really well for this one is because when you do L'Hopital's rule, it cancels itself out. Let's say you try to compare it to 1 over n squared. What'll end up happening is the limit test will fail. You'll get something that doesn't work, or something that goes to infinity, or something that's less than 0. You'll get something that doesn't work. When it doesn't work, you have to try something else, or just fix what you tried it to. Because if you picked 1 over n squared, that would converge, and we know this function diverges, so therefore it won't be both. So that's how you'll know if you picked the wrong thing. Two more. This one.
The test for divergence for the.
So the test for divergence, to work, you basically are going to have to say that the top is getting bigger faster than the bottom. And I'm going to go out and let me go 5 to the end. It's going to get much bigger than n squared. So remember, if they were all raised to the nth power, we could use the root test. But this one, I have a mixture of them. So I can't really use the geometric series because I, again, don't have everything raised to the nth power. So the geometric series and the root test kind of helps do very similar things. The root test will solve the more complex problems. I can't do a P series because of the 5 to the n. So what do you want to try? Okay, the two tests that we have for absolute convergence are root and ratio. So which one do you want to use? The root test, they all have to be raised to the nth power to get rid of it. This one they don't. So this one you want to use the ratio test. The ratio test is actually probably one of the more useful ones because you're literally just doing the next term in it. So it's easy to figure out. If it doesn't work, then we can try something else. But so in the ratio test, we're looking for the a to the n plus 1 over a to the n. So I have n plus 1 squared plus 1 over 5n all over n squared plus 1 over 5n. All right, so let's clean up and deal with the thing on the top. And then we can do the cube change flip part all at the same time. So I have n squared plus 2n plus 2 over 5n times 5. Not 5n, 5 to the n. Times 5n over n squared plus 1. So that goes to, I cancel out the 5n's. So I get 1/5, which I'll just pull out, n squared plus 2n plus 2 over n squared plus 1. Pi. All right, so the n squared plus 2n plus 2 over the n squared plus 1 goes to what? 1. So this whole thing goes to 1/5, right? So now the limit or the ratio test says is I'm comparing it to what? The root and the ratio test compared to what? So this is less than 1, so that means it converges. All right, last one. You're thinking along the right lines. I appreciate that. The problem is I can't make that raised to just the k power. So doing the kth power of that doesn't get rid of the k's. So good thought. Everything was raised to the k. That was a good, very good first thought. And I probably, if I didn't say that, I would have seen this on the test. And then said, yep, that's less than 1. We're good. Probably would have seen that. Yeah, you can't do that, unfortunately. The funny thing is, this actually goes back to something Scott said earlier, and we couldn't do it for the problem he said it. You can, if you're going to divide everything, like it's all with k's. So I can actually take everything in this problem and divide them by 4k. The reason I can do that is you're going to see in a second. It's not solving my problem, but it's allowing me to pull the k out, basically. So what this gets me is 5/4 k over 3/4 to the k plus 1. So what it gets me is it gets me fractions that I now can look at in terms of the geometric series on what they do. Okay, so if I had 5/4 k as s goes to infinity, what happens to that? This is going, if this whole thing, if I'm just doing the limit as k goes to infinity, the top's going to what? Infinity, right? What's 3/4 k is going to? It goes to 0, because that's a geometric series and the ratio is less than 1, right? So that's going to 0. So that's 0 plus 1, which is 1. This is not an indeterminate form. This goes to infinity, which means this is divergent based on the test for divergence. Because the limit of it goes to 0, goes to infinity. It doesn't go to 0. I wanted to do one that used the test for divergence that wasn't very obvious that it was the test for divergence. You could have also probably done this one with a limit comparison test, comparing it to 5/4. Okay. Because as the 4K gets infinitely large, the 3K kind of drops off. So you can just look at it as 5/4 and compare it as a geometric series. So we could have done this. We could have said that 5 to the K over 3K plus 4K. Actually, that's going to be less than 5/4. Okay, so actually it wouldn't have worked. We would have to do the limit comparison test in that situation. We couldn't just do the direct one because the bottom is getting larger, so that's obviously going to be smaller than that. So we would have had to do the limit comparison test for this one if we wanted to. And it would have worked out. It just would have been more work. So, all right, we're done. I have copies of the test. So you can come grab it.